we are now going to look at the other type of transformation that we're really interested in. And so that's where we've got multiplication or division by a number, either inside or outside the function. And so these are going to lead to stretches or compressions. So as opposed to like just taking the object and moving it, you're actually going to, like a rubber band, like fix a part of it and then like pull it out so it stretches, or squeeze it down, or like a spring, for example. So we're going to look at what might be some familiar functions, just the square functions, and then just see what happens when we do either in B, multiplication outside of the square by 2, and in C, it's actually multiplication inside the square by 2. So we'll start with the x squared. Hopefully you kind of remember what this graph looks like. If not, just plotting a few points like this is fine. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9. Negative 1 squared is 1 because the negatives cancel. Negative 2 by negative 2 is positive 4. Negative 3 by negative 3 is positive 9. And so I will draw my points: 0, 0, 1, 1, 2, 4, 3, 9, negative 1, 1, negative 2 and 4, and negative 3 and 9. And as best as I can with this pen, I'll try to connect these. It's a lot harder than graphing freehand with the actual pen and paper, but yeah, that should be it. And I'm just gonna faintly, maybe in the lighter blue, draw the same curve on the other axes, just so I can do my comparison. Oh, that's not right. That was supposed to be an arrowhead. It didn't look very good. And same thing over here. Just because I think it looks like I might have squeezed my y-axis a bit for these two graphs, so I want to make sure we can really compare those shapes. Oh, that looked good. Okay. There, it doesn't look symmetrical, but yeah, you know, it's a parabola. All right, so this is, again, these are just y equals x squared for both of them, not the graph I'm actually trying to do. Okay. And I'll label this one also as y equals x squared. All right, so for B, we can see that we've got that multiplication of 2 on the outside. I'm going to do this one without any work. Essentially, it's x squared times 2. I can literally just take all the values I just found and double them. And so mathematically, that's kind of the point. So maybe I'll do the rough work. So that would be 2 times 9. This will be 2 times 4. It's capping off all those equals. I don't like that. Two times 1, 2 times 0. Two times 1, 2 times 2 squared, 2 times 4, and 2 times 9. And then I can work out all of those numbers. 2 times 9 is 18, 2 times 4 is 8, 2, 0, 2, 8, and 18. So you can sort of see the same symmetry in the answers around 0. And if you look, or you can even just look directly at the calculations, you'll see it's exactly double of everything we had in A. And so if I plot all of these points, I will get, there's my 0, 0, and then 1 and 2, 2 and 8, which should go up about here, and then 3 and 18, that's going to be a little too high off the graph, so I'll leave that for now. Negative 1 and 2, and negative 2 and 8. And again, the negative 3 is a little too high for me. So I should be able to plot these guys. And so if we look at this, there's two perspectives on how we could look at this. One thing visually, probably what would jump out at you first is that it actually looks like it's been sort of squeezed together, like from left to right, you've sort of just squeezed it inwards. Technically, yes, but I'll talk a little bit more about that in C. Another way that we can look at it is that what we've actually done is doubled all of the heights. And that's literally what's happening, because what we've done is we've taken the y's and we've turned them all into 2 y's, right? 9 became 18, 4 became 8. So we've actually doubled all the y's. So this is a vertical stretch. By 2, by a factor of 2. So we could think of it as a compression, but the compression number is a little bit awkward. So don't think of it as a compression. But that would be horizontal. So, and the only reason why is because it's a really particular type of function, and I will talk about that in C when we wrap C up. So for C, I'm gonna, I guess, do the calculations. So here, what we're gonna have, if I plug in -3, I'll actually get -6 squared. And I plug in -2, I'll get -4 squared, right? So everything's happening before the square, and that makes a really big difference. -2 squared. We'll do the calculations after. 0 squared, 2 squared, 4 squared, not 9. Ugh. There we go, 4 squared and 6 squared. So -6 squared will be +36. -4 squared is 16. -2 squared is 4, 0, and then 4, 16, 36. And so I'm going to plot these points in pink. So I have 0, 0, and 1 and 4, -1 and 4, and 2 and 16. I think I gave myself just enough space to be able to plot this. And -2 and 16. Okay, and so this is my graph of that 2x squared. I'll just go back and label this one, I forgot. And so it looks kind of similar to the graph that I had in B there. It looks like I could have pulled it upwards to get this new graph. Now, if you look at the pulling upwards, it's not by that number 2. If you were to pull it upwards, it would actually be up by 4. And the reason is we could simplify this as we distribute that square to both the multiplicative parts. This is the same graph as actually 4x squared. And the same thing on the left here, we could have actually packaged that all inside of a bracket and wrote like √2x squared if we wanted. And that way the multiplication would be inside the bracket instead of outside. This one we could have written it with the multiplication outside instead of inside. But if we want to think of this multiplication inside the bracket, we want to think of it horizontally. And then what we're actually going to see here is that everything's actually horizontally cut in half. So what we're actually getting is a compression horizontally, which means the x values. And by a half, all of the x values are getting cut in half. So we have a horizontal compression. And then I'd say by, you can either say a half or 2. It really depends on what literature you're reading. For all the web work questions, I let you submit as many times as you like, so I'm not trying to trick you on this or anything. I like to say a compression by 2, basically, because it's essentially, sorry, I usually like to actually write a compression by a half. Doesn't matter because everybody asks for something different. I just like to write the number that you multiply by, basically. All the x's get multiplied by a half, and because that number is small, less than 1, it does actually make a compression. And so, yeah, you'll get something that kind of looks like just squeezed together, essentially. That's what a compression does. If it had been a horizontal stretch, it would look pulled apart, and you just write the multiplicative number. So just a conclusion for these is if we have y equals, and I'll use the same letters that we typically see, a, f, b, f of bx, then the graph of y equals f of x gets will be, or gets, let's say, vertically stretched by a. So all of the y's become a y's. You can actually go through point by point and multiply all of those y values by a y. And horizontally compressed by, and again, it's the opposite, just like with the shifts, it's the opposite of what you expect sign-wise. Multiplication by b is actually going to be 1 over b. So your x's are going to go to 1 over b. You actually divide by that number, even though it looks like multiplication right in front of you. So x is going to go to 1 over bx, and then same deal if it is, if a is less than 1, so if a is small, it's actually going to be a compression. So I'm writing this very small at the bottom here. And if b is less than 1, then 1 over b will be fairly large, and so you'll actually end up getting a stretch. You don't even need to really think of the word stretch or compression, though. Like you just take the y and either multiply by a or divide by b, and that's how you generate your new y's. So don't get too fussed up by the language being used. So we'll do an example of one of these, and then we're going to put everything together. Okay, so for this example, I didn't try to come up with a nice application or anything. It'll just be a bit more of a straightforward graph some transformation type example. So I've given you this graph of y equals f of x, kind of a weird looking piecewise function. And there's a couple of features that are going to be annoying. We've got that open dot at, what are the coordinates there at? -1 and 2. And then we've also got sort of it's not a straight line from 0 to 2. So that's going to be, a little annoying to deal with. So we just need to make sure we kind of follow through with that when we draw our stretches. So I'm just labeling the rest of the points here. And I've kind of set up on the other two graphs the sort of ghost graph for f of x that we need to push around. And so we're going to do a couple of, stretches, compressions on these two graphs, just depending on what the numbers are. You'll notice I also threw in some negatives to both of these. A lot of times when you learn this, they'll teach you the negatives completely separately, but negative is just multiplication. It's multiplication by -1. So I don't see why we shouldn't just treat that the same as we do all the multiplications. It's going to behave the same way. So why learn a third thing when you could just lump it into one of the other two? So we're going to go through here and label the two things that are happening. The way that we'll typically write things is going to be such a way that you can always work left to right. So if you're wondering if it matters if we do the outside or the inside first, if you write things a certain way, it doesn't. So the way it's written right now, we're actually okay. And the inside outside things don't interact with each other. So it won't actually matter for these first couple that we're doing. So if you remember that half, that's on the outside. So it's going to affect all our y values. And it's going to do exactly what you think it should do to the y values. It's a half times, so it's going to multiply all of our y values times a half. And then this thing on the inside, this is the same thing as writing -1 times x. So what we could do is say that the x's become x divided by -1, which is actually just -x. So all the x's become their own negative. And so I'm going to do this one in 2 stages because I don't think we've, at least not in this lesson, I haven't gone over any of these 2-parters. So first of all, I'm going to take all the y's and cut them in half. So this is y equals 0, and it'll stay at 0. This is y equals 2 at the open dot, so it's going to go down to 1. And then this dot at 0, 1, it's going to go down to a half of its height, so at a half, and then 0 stays at 0. So those are just the y values that are affected. And then I need to sort of follow through with any curves that are drawn and connect those. And so the green one, that light green, is actually just the function a half f of x, which is not my finished product. So I'm going to use the darker green for the finished product. And so finally, I'm going to do this action that I said I'm supposed to do here. I'm going to take all the x's and multiply them by -1. So the leftmost point is at x equals -2. And I'm working from the green ones now. So -2 is going to flip over and go to +2. This one at -1, the x value is just going to flip over and become +1. And I can connect those dots because I know it's supposed to be. And then I've got x equals 0. Well, -0 is still 0. And then I've already shaded it in, but there was a point here at 2 and 0, which is now going to go to -2 and 0. And so now I would connect those dots there. So I'm going to try to make that green one a little bit more prominent so it's the most visible thing on this picture. But yeah, so that dark green curve should be basically what my finished product looks like. That's the one I want. So one way that you can look at this is just sort of point mapping. So if we started with all of the points drawn here, so we started with -2 and 0, and -1 and 2, and 0 and 1, and 2 and 0. Then the first action that I had was y goes to a half y. So I would just take all the y's, which are the rightmost entry there, and they're all gonna just get cut in half. So 0 does nothing, 2 goes to 1, 0 goes to a half, and 0 stays at 0. And then again, follow the action. The next one is that my x's go to -x. And so I'll just take all the x's and flip them. So this is one way of getting your points without maybe having to draw stages to the graph. Then I would just kind of use the first graph to guide how I put everything together. I do recommend, if you're going to use this point mapping approach, be really, really careful. It's pretty easy to make fairly small calculation errors. I actually made one. I'm not sure if you're noticing it at this point here is not right. I just caught it. That should have been -2 and 0. It's super easy to make those errors. And because you don't have this picture that's flowing around in a semi-natural way, you won't catch those errors by looking at them as easily as you can with the graph. So you would just plot these things and then probably have trouble putting it together because it's not sort of fitting in with the plots that you see in the original function. So I do recommend be really careful with this, even though it's less drawing. So yeah, you'll see there the effects of the minus. If you have a look at basically what it is, it just sort of flips the image like a mirror image over the x-axis. And we'll get something similar for the minus in B over here. The minus on the y is going to be a vertical reflection. So you multiply the y's by a negative, well, in this case 3, not 1, but yeah. All right, so this one I'll use a different color scheme. Let's go with the pinks, maybe, and then that dark red color. So I'll start with this one. And so my y's are going to go to negative 3y. And then my x's, well, I could rewrite this. Again, this is the same thing as a quarter times x. And so what's going to happen here is my x's are going to go to x divided by a quarter. And that's the same thing as 4x. All right, so I'm just going to look at my y's and do the multiplications. I'm not going to write out all the point mapping this time. Y is 0 times negative 3 is 0. 2 times negative 3 is negative 6. So you can see that flipping taking place. Things that are on the top are now going to the bottom. This third point is at 1, so it's going to be 1 times negative 3 is negative 3, and then 0 times negative 3 is 0. And so I'm going to try to follow the trend in the graph there when I connect these dots. It looks okay. So something like that. The one on the right is a little bit curvy, so I don't want to use a straight line to draw it. I don't know quite how it's going to look. Something like that. It's not the best, but it's got some curve to it. So that second graph is going to be just the graph of negative 3 f of x. And then what I'm going to do is now multiply all those x's by 4. So x equals negative 2 is going to go all the way to negative 8. The next one would be x equals negative 1. So it's going to go to negative 4. So now notice when I'm changing these x's, it doesn't do anything to the y values. I'll just connect the dots here. So I know that should be a straight line. No, I didn't quite connect it. I'll just color that in there. Yeah, so this horizontal stretch that I'm doing right now, I've already affected the y's, so all these things are just moving laterally. X equals 0 stays at 0. Right, 0 times 4 is still 0, and then 2 times 4, so this point here is going to go to 8. And again, that's just the x value that's moving there. And then I'll do my best to draw this kind of gentle curve. And so that should be more or less what it looks like. So again, I'm going to try and make this a little bit bigger so you can see the finished product better. It's hard to do with a steady hand. And I'll try another one here. And so yeah, that burgundy one is my finished product. So y equals the whole thing, negative 3 f of x over 4, like this. Yeah, so those will be your stretches, as well as a little bit of reflections thrown in there, just because the operation's all the same. Usually, like visually, I tend to not really actually think of these things as stretches. I think of take the x's and multiply them by this number, or take the y's and divide them by this number. You'll also see the trends. We have that x divided by 4. Remember, it does the opposite. So what that actually does is it pulls it apart horizontally. It does make sense to do that with this function, for example. So why that actually makes sense is because if we go through right now and look at the value of, let's say right here, we look at that point. Let me choose a different point. I'm going to choose something. Don't want one with the 0. Actually, yeah, the 0 is fine. So yeah, so if we look at this and we want to plug in x equals -8, so what I would have is y equals -3 f of, plug it in for the x into this function, not the original one, -3 times f of -8 over 4, which is -3 f of -2. And so to get that f of -2, what I would do is go and look all the way at the original function, and that is that point there at -2, which has an output of 0, because that's the original function. So there's my -3 times 0 equals 0. That's what my graph says it equals, right? So that's what I want it to do. And again, it's because what's happening here is this point that I'm trying to find, the corresponding point on this new graph is actually coming from x over 4 equals that input of -2 to get that output of 0. And so how do we solve this equation? Well, we do it by multiplying. We multiply that -2 by 4. So everything that's going on inside that function is sort of opposites because you're trying to unravel an equation. So that's going to be useful in the one last discussion that we'll have over these transformations.